everyone, thank you for joining this video. Today we're going to be learning about shapes of molecules and ions. So these are the learning objectives. We're first going to look at the difference between bonding pairs and lone pairs, and we're going to look at the electron repulsion theory. We're also going to look at the shapes of molecules and the bond angles, also labeling the shapes up to 6 electron pairs. Okay, so the first thing to know is the electron pair repulsion theory. So this basically states that electron pairs repel each other as far away as possible. So around a central atom, they will be as far away from each other as possible to arrange themselves around the central atom. And this makes sense because electrons are negatively charged. So if you put 2 electron pairs together, they will naturally repel each other. And so that's why they want to be as far away as possible from each other. So molecules and ions possess 2 types of electron pairs. They possess bonding pairs and lone pairs. So bonding pairs are pairs that have been bonded with something else. So, for example, in chlorine, one of the electrons from each has been covalently bonded to the other one because they share a pair of electrons. The lone pairs would be the pairs of electrons that don't do anything. So they're just excess, basically. So they're not bonded to anything. So they're just there. And because the electron pairs repel each other, the shapes of molecules are a consequence. So it depends on how many bonding pairs they have, how many lone pairs they have. And one thing that's very important is that lone pairs repel a lot more than bonding pairs. So the greatest repulsion comes from lone pair, and then second would be bonding pair, lone pair, and then bonding pair. So now we're going to look at shapes of molecules. So we're going to start off with the simplest one, which is 2 bonding pairs, 0 lone pairs. So an example of this would be carbon dioxide. Now, carbon dioxide actually looks like this. But when we're working with shapes of molecules, these double bonds actually only classify as 1 bonding pair. So a double bond is also equal to 1 bonding pair. So it only counts as 1 bonding pair. And this is the general kind of format of a molecule which has 2 bonding pairs and 0 lone pairs. So we have one atom in the middle, and then 2 of the same element on the outside. And because it's shaped like this, we call it linear, which makes sense because it's like a line. And so it's 180 degrees, which makes sense. So the next few that we're going to look at is when they have 3 pairs of electrons. So the first one that you can get is 3 bonding pairs and 0 lone pairs. So you have an atom in the middle and then 3 of the same atom on the outside. And because of electron repulsion theory, they repel each other by the same amount because they're all bonding pairs. So they want to be as far away from each other as possible, but they also repel each other from by the same amount. So that's why it's 120 degrees is the bond angle, because a full circle would be 360, and because you've got 3 of the same atom, they repel each other by the same amount, and so one of these angles would be 120 degrees. And this is also a 2D shape, the same as the first one. So the name of this one is trigonal planar. So basically triangular, and then planar meaning like 2D. If we add a lone pair, and so we've only got 2 bonding pairs, and if we add a lone pair, then it becomes bent. An example of this would be sulfur dioxide, and the angle actually changes by 2 degrees because the repulsion from a lone pair is bigger than from a bonding pair. So that's why this angle decreases from, it was 120 degrees before, but now it's become 118. And that's called bent, sorry. And now we're going to move on to 4 pairs of electrons. So the first one is 4 bonding pairs and 0 lone pairs. So the shape of this is basically a triangular pyramid. So it's got 3 on the bottom and 1 on the top. And these just signify that it's 3D. So this kind of means that it's kind of behind the shape and this is kind of in front. So just imagine a triangular pyramid like this. That's what it looks like. So you've got Q here and Q. And then A would be somewhere in the middle, kind of bonded to all 4 of them. And the angle is 109.5 degrees, and we call this tetrahedral. We then have 3 bonding pairs and 1 lone pair. So we've added the lone pair at the top, and we've only got 3 bonding pairs left on the bottom. So this has become sort of a squished kind of triangular pyramid. And this angle's changed from 109.5 to 107. So for every lone pair we've added, we minus 2.5 degrees from the angle because there's more repulsion from it. So this is called trigonal pyramidal. And then the next one is 2 bonding pairs and 2 lone pairs. So the 2 lone pairs are at the top. And then these 2 are the bonding pairs. We've minus 2.5 degrees from the angle again, and we call this bent. So this is similar to the bent that we saw before, but this one is 2D and the angle is 118 degrees. And this one is 3D, but the angle is 104.5 degrees. So they are different. The next one we're going to look at is 5 bonding pairs and 0 lone pairs. So what this looks like is basically 2 triangular pyramids stacked on top of each other. So you have one upside down and the other one upright. So this angle here is 90 degrees because it's just because of the way it's shaped, and because this bit is like the planar bit, the triangular bit. So if you divide that whole circle by 3, it'll be 120 degrees because they all repel each other by the same amount. And this is called trigonal bipyramidal, which basically means 2 triangular pyramids. And for an example of this would be phosphorus, I'm not sure how to say it, PF5. And the next one is 4 bonding pairs and 1 lone pair. So we have the lone pair at the top and then the 4 bonding pairs. So this is kind of similar, but we've lost one of the atoms at the top, and this plane here is slightly closer to the bottom. So that's why this angle here is decreased by 1 degree. It's now 89 degrees. And this has also decreased by 1 degree, so it's 119 degrees. And we call this T shape, which kind of makes sense because it kind of looks like a T. And then we have 3 bonding pairs and 2 lone pairs. So we have the lone pairs at the top and the bottom, and this now kind of becomes planar. So because it's planar and they all repel each other by the same amount, we have 360 divided by 3 again, so we get 120. And this is called trigonal planar. Now we move on to 6 bonding pairs and 0 lone pairs. So this is 2 square-based pyramids on top of each other. So we have 90 degrees between everything, and we call this octahedral. If we then exchange a bonding pair for a lone pair, and we put it on the bottom, we get a square pyramid, but with the bottom slightly raised. So that's why this angle here is 89 degrees instead of 90. And we call this square pyramidal. And then the last one is with 2 lone pairs and 4 bonding pairs. So it becomes planar again. And the angles are 90 degrees, which makes sense. Because there's 4 of them. And 360 divided by 4 is 90. And then we call this square planar, because it's a square and also because it's flat. How to work out the shape of a molecule. So the first thing you do is you decide on the central atom, and then you draw the central atom with its outer electrons, and then you bond the other atoms with the central atom like we did for dot and cross diagrams, and then we count the bonding pairs and lone pairs, and then you look at the shapes above and match it. So obviously for the exam you'd have to remember all the shapes. Maybe at the start of the exam paper, maybe kind of doodle them down, just so you know that they're definitely there. A quick note again that a double bond counts as one bonding pair. It's very easy to forget that. So we're going to look at this example. Draw the shape of a H3O plus ion. So first we start off with deciding on the central atom. So because we've got 3 hydrogens and an oxygen, I think it's probably safe to say that the oxygen will be the central atom. So we have an oxygen, and the oxygen is in group 6, but it's a plus ion, which means that it's lost an electron, so it has 5. So 1, 2, 3, 4, 5. And then each hydrogen has 1 electron. So you can see that it's going to be a covalently bonded ion because they're both non-metals. So that means that a hydrogen would be here and it'd share its electron. Like that. And so now we've got the full dot and cross diagram. And now we just count the bonding pairs and lone pairs. So we've got 1, 2, 3 bonding pairs. And we've also got 1 lone pair. And if we have a look back at the shapes that we learned before, this actually corresponds to a trigonal pyramidal. So the one which is a triangular pyramid but slightly squished. So it looks like this. Here are the 3 hydrogens. And then this is the lone pair. And this angle should be 107 degrees. And it should be trigonal pyramidal, because it's been deducted from 109.5, which it would be if it didn't have this lone pair and it was just a tetrahedral. Now we're going to have a look at some questions. So the first question is to explain why NF3 has a different shape from BF3. So first we're just going to look at the periodic table and see where everything is. So nitrogen is in group 5, so it has 5 outer electrons. And boron is in group 3, so it has 3 outer electrons. And fluorine is in group 7, so it has 7 outer electrons. And because they're all non-metals, that means that they go through covalent bonding. And we can see that fluorine requires one electron to form a full outer shell. So with the BF3, that means that one of these electrons are shared with each of the fluorines. So we have boron in the middle, and then 3 fluorines on the outside. And then the rest of the fluorines, which aren't shared in the covalent bond. And then the electrons of the boron. Boron is a bit of a weird one, so we can actually have 6 electrons in the outer shell and not 8. So this has now got a full outer shell, and this is how it's covalently bonded. Whereas if we look at NF3, if we bond 3 fluorines to nitrogen, we get this. So we have the nitrogen in the middle, and we have the 3 fluorines like we did for boron, and then we share 1 and have 6 on the outside. And then for the nitrogen, we have the 3 which are shared with each fluorine, and then we have 2 left. So that means that they have different shapes, because this one has 3 bonding pairs and 0 lone pairs. Whereas in NF3, we have these 3 bonding pairs, but we also have this pair here, which is 1 lone pair. And so this forms a trigonal planar molecule, which looks like this. So you'd have B in the middle, and then the F's, and then these would be 120 degrees because there's no lone pairs, so they repel each other by the same amount. And then this one is 3 bonding pairs and 1 lone pair. So this would be trigonal pyramidal. So this looks like this. So it's got nitrogen in the middle, and then the fluorines, and this is a 3D one. So that's when we draw these symbols. And then we have the 1 lone pair here. So if it was 4 bonding pairs, the angle would be 109.5 degrees. But because there's 1 lone pair instead of one of the bonding pairs, that means that there's more repulsion from this lone pair. So this angle decreases from 109.5 to 107 degrees, because it decreases by 2.5 degrees every time a lone pair is added. So for number 2, draw the shape of an NO3 minus ion. So there's a nitrogen, so that's in group 5. So it has 5 electrons in the outer shell, and then oxygen, which has 6. So if we bonded 3 of these oxygens to a nitrogen, we'd have something that looks like this. Nitrogen, and then an oxygen here, another oxygen, and an oxygen here. And then we'd probably form a double bond with 2 of them and a single bond with the 3rd. So we would get this because nitrogen has 5, so it can share 5. So I've shared 5 here by using 2 double bonds and a single bond. And this means that with the oxygens, this one now has 4 left. And this one also has 4 left. And this one has 5 left. But then we have a look and see that it's a 1 minus ion. So that means that there is an extra electron on this oxygen here, which makes it into an NO3 minus ion. And so we can see that it's got 2 double bonds and a single bond. So there are no lone pairs because there's none on the nitrogen. Doesn't matter about these oxygen ones. There's none on the nitrogen. So that means that there's only 3 bonding pairs because double bonds count as bonding pairs. So we have nitrogen and 3 oxygens. And this should be 120 degrees. And this is called a trigonal planar again. Hi everyone, thanks so much for joining me for this video. We're going to look at a harder question for the topic of shapes of molecules. So the question is to predict the shapes of the SF6 molecule and the AlCl4- ion, to draw diagrams of these species to show their 3-dimensional shapes, to name the shapes and suggest values for the bond angles with reasoning. So we start off with the SF6 molecule. So sulfur is in group 6, so it has 6 outer electrons. And then fluorine is in group 7, so we know it has 7 outer electrons. So if one fluorine was bonded with one sulfur, one of these electrons would be shared. One of the sulfur electrons would be shared with the fluorine, and this fluorine electron would be shared with the sulfur. And this would be how it would bond. So it would be a covalent bond. So because we have 6 of them, all of these electrons will be shared with fluorines. So it would look, the dot and cross would look like this. 2, 3, 4, 5, 6. These would all be fluorines, and they would all give an electron each. And they would still have their 6 on the outside. So then we count up the bonding pairs and the lone pairs. So we don't have the lone pairs, we only have bonding pairs, and we have 6 of them. So we must have 6 bonding pairs and 0 lone pairs. I always write this at the side so it reminds me of what I have. And then I think back to the shapes of molecules that we learnt. And then I remember that this forms an octahedral shape. So you'd have sulfur in the middle, and then fluorines here, and also behind like this, and then one at the bottom. And the angles would be 90 degrees everywhere. And we know that this is called octahedral. And for explaining your reasoning, it's because there's no lone pairs. So all the bonding pairs repel each other by the same amount. Due to the electron repulsion theory, how all the electrons want to be as spaced out as possible because they repel each other. And so if they all repel each other by the same amount, then every angle will be 90 degrees because there are 6 atoms arranged around one central atom. So basically these 4 are in a plane, and these 2 are 90 degrees to that plane, and all of these are 90 degrees from each other. So it's kind of like a square, and then so it's basically 2 square pyramids on top of each other. And then we look at AlCl4-. So aluminium is in group 3. So it has 3 outer electrons, and then chlorine is in group 7, so it has 7 outer electrons. So when we bond 4 chlorines to aluminium, we then get something that looks like this. Two, 3, 4, and these all give share one electron each, and the aluminium also shares 3 that it has. But then one of the chlorines, it means that both of the electrons have to come from the chlorine because aluminium has no more electrons to share. And then these still have 6 on the outside. This one has 5, and this one has 6, and this one also has 6. But it's an AlCl4- ion, which means that there is an extra electron here. So this has formed a dative covalent bond where both of the electrons have come from the chlorine and none from the aluminium, and this whole thing is a minus ion. And so when we look at the shape of it, it looks something like this. Because actually a dative covalent bond is still classed as a bonding pair. So there are still no lone pairs, so it's 4 bonding pairs, and this makes a tetrahedral shape. And these angles are 109.5 degrees, and that's the triangular pyramid.